Today we're going to focus on student development in grades 6 through 12 and why development matters for math instruction. In a graduate context, I want to be explicit about what we mean by development. We're talking about cognitive development, social and emotional development, and the development of learning behaviors like self-regulation and persistence. When instruction aligns with how students are developing, students are more likely to access the math, engage with the tasks, and make meaningful progress. I also want to connect development to how we plan lessons. One major idea in effective math instruction is content coherence. Coherence means lessons are organized so ideas connect logically and build toward a clear mathematical point. When lessons are coherent, students can see how today's work fits into what they already know and where they're headed next. When lessons are incoherent, the learning can feel like disconnected activities, and students often struggle to explain the purpose of what they're doing even if they can complete individual steps. So as we talk about development, keep in mind that development and coherence work together. Development influences what kinds of connections students are ready to make, and coherence is how we structure the learning, so those connections are actually possible. Let's begin with developmental milestones for grades 6 through 12. These milestones are not strict rules and they don't apply identically to every student, but they are helpful patterns. In grades 6 through 8, many students are in the middle of a transition from more concrete reasoning toward more abstract reasoning. A useful frame here comes from Piaget. In the concrete operational stage, students tend to reason best when ideas are tied to concrete representations and visible relationships. As they move toward formal operations, they become more capable of thinking hypothetically and manipulating symbols without relying on physical or visual supports. In practical terms, this helps explain why many middle school students can handle procedures, but struggle with algebraic generalization, unless we intentionally bridge the gap with representations, context, and structured reasoning. This is also a stage where social and emotional development has a strong effect on classroom learning. Adolescents are often highly sensitive to peer perception and status, and that can influence risk-taking in math. A student may avoid participating or asking questions not because they don't care, but because the social cost of being wrong feels high. That matters instructionally, because classrooms that treat mistakes as normal parts of learning tend to increase participation and persistence. From a theoretical lens, you can connect this to self-efficacy. Bandura's work emphasizes that students' beliefs about their capability influence effort, persistence, and willingness to engage with challenge. So when we normalize mistakes and provide feedback that emphasizes growth and strategy, we're not just being nice. We are supporting a developmental need that directly affects learning behavior. In grades 9 through 12, students are typically more capable of abstract reasoning, extended problem solving, and justification. Many students can work with hypothetical scenarios and can evaluate whether an argument makes sense. They are also developing metacognition, which is the ability to monitor their own thinking, recognize when something is not working, and adjust their approach. However, students vary widely in readiness, and high school classrooms often include students who are still developing the same conceptual foundations. So development cannot be treated as a simple grade-level assumption. It has to be treated as a classroom reality. Now let's talk about the role of developmental needs in math instruction. This is where theory helps us justify the instructional choices we make. One major concept here is the idea that students learn best when instruction connects to what they can do now and supports them in moving to what they cannot yet do independently. Vygotsky's concept of the zone of proximal development explains that learning is most productive when tasks are just beyond a learner's independent ability, but achievable with support. This is a strong theoretical foundation for scaffolding, modeling, guided practice, and strategic use of peer collaboration. It also explains why instruction that is too difficult or too easy can reduce learning. If tasks are far beyond students' readiness, they disengage. If tasks are too simple, they don't develop new capacity. Bruner's spiral curriculum also helps us think about developmental needs and content coherence at the same time. The spiral curriculum emphasizes revisiting major ideas over time at increasing levels of complexity. That connects directly to coherence because it encourages lesson sequences where concepts reappear and deepen rather than appearing once and disappearing. Developmentally, that repeated exposure matters because students may not be ready to fully internalize an abstract concept the first time they see it. The spiral approach allows students to build meaning gradually as their reasoning becomes more sophisticated. Kolb's experiential learning theory adds another helpful lens, especially for adolescents. Kolb emphasizes learning through concrete experience followed by reflection and conceptualization. In math instruction, that can look like students working through a task, analyzing what happened, and then connecting it to formal mathematical language. This helps explain why doing a problem is not enough. The reflection and connection step is what turns activity into learning. It also connects back to content coherence because reflection is where students see the thread that links one idea to the next. Now let's shift into strategies for addressing developmental differences in math classrooms. The goal here is not to create separate lessons for every student. The goal is to design instruction with multiple access points, clear progression, and opportunities for students to engage at different levels. One core strategy is using multiple representations. This means representing mathematical ideas in more than one way, such as graphs, tables, verbal explanations, visuals, manipulatives, and symbolic notation. Developmentally, this supports students who are still transitioning into abstract reasoning because it bridges concrete understanding to symbolic understanding. It also supports advanced learners because translating across representations deepens conceptual understanding and improves transfer. A second strategy is scaffolding, and this is where Vygotsky's zone of proximal development is particularly useful. Scaffolding means we provide temporary supports that help students successfully complete tasks they could not yet do alone. Those supports might include worked examples, partially completed problems, guiding questions, sentence stems for explanations, or structured peer discussion. Then we gradually remove supports as students gain independence. This aligns with developmental needs because it supports competence without removing cognitive demand. A third strategy is designing learning as coherent sequences instead of isolated activities. This is where content coherence matters. A coherent lesson is structured so that each activity builds toward a clear conclusion. In math, that often means the opening connects to prior knowledge, the core task introduces a new idea with purpose, and the closing brings the learning together so students can articulate what they learned and why it matters. For students in grades 6 through 12, coherence is especially important because it reduces cognitive overload. When the lesson is structured like a story with a clear progression, students can focus on the math rather than trying to guess why they're doing each step. Another strategy is flexible grouping. Developmental differences do not align perfectly with age or grade. Flexible grouping allows teachers to respond to readiness in the moment. This can include small groups for reteaching, groups for structured practice, or groups for extension tasks. Vygotsky also supports the value of social learning here, since interaction with peers can provide the kind of support that moves students forward, especially when peers are slightly more advanced in a specific skill or way of thinking. Choice and relevance are also important, especially in high school. Adolescents often respond well to autonomy and meaningful purpose. When students have choices in how they practice or demonstrate understanding, they have more ownership and engagement. When tasks connect to real contexts, students are more likely to see value in what they are doing. This can be tied back to motivation and self-regulation, and again to Bandura's emphasis on self-efficacy. When students experience success on meaningful tasks, their confidence and persistence grow. Now let's talk about analyzing the effectiveness of instructional strategies in addressing diverse developmental needs. In a graduate course, we want to be clear that effectiveness is not only about test scores. Effectiveness includes access, engagement, reasoning, and growth. One way to analyze effectiveness is to look at access. Are there clear entry points for students who need more support? Are there extensions for students who are ready to deepen or generalize? If not, the strategy may be appropriate for some students, but not responsive to the full range of developmental needs in the room. Another way to analyze effectiveness is to look at student thinking. Are students able to explain their reasoning? Are they making connections between representations? Are they able to describe what they learned and why it works? These are indicators that instruction is supporting conceptual development, not just short-term procedures. We also look at student engagement and persistence. Are students willing to attempt challenging tasks? Do they ask questions? Do they revise their thinking when they make mistakes? Those are developmental indicators tied closely to classroom culture and self-efficacy. If students shut down quickly, avoid participation, or view mistakes as failure, that often suggests the instructional environment is not supporting key developmental needs, even if the content is technically covered. Assessment data matters, but it is most useful when combined with observation and reflection. Patterns and errors can reveal where students are in the concrete to abstract transition. For example, students may be able to solve a procedural equation, but struggle to explain why the steps work, which signals that the concept is not yet internalized. That kind of analysis helps you adjust instruction with intention rather than guessing what students need. To close, development, coherence, and instructional strategy belong together. Development helps us anticipate how students are likely to engage with math. Coherence helps us structure learning so ideas build logically and students can make sense of the content. Theory helps us justify why certain strategies work and how they support learners at different stages. When these pieces align, we create instruction that is not only standards-based, but also developmentally responsive and genuinely supportive of diverse learners.